All right, students, I hope I'm audible. I hope I'm audible to you. If yes, please respond somewhere in the chat box. I hope you can listen to me. Yes, okay, I got the answer. So that's great. So after a long time, again, we are on online mode. And today's session is focused on some of the numerical solutions of the questions that we have to complete. Today we are going to conclude unit load method, and we are slowly moving to the next topic, that is influence lines diagram. I know that you are already exposed and aware about it, but however, uh, I've been informed that you did ILD for determinate structures, right? So I'll need to check your existing way of understanding of ILD, why it is used and like that. And introductory part will be again discussed. And then we'll discuss how to create ILD for indeterminate structures. However, we'll touch only the specific type of the structures where the propped cantilever will be discussed, and in the other part the continuous beam will be discussed with the standard load cases like UDL and point load and combination of them. So that is the target of next class. But in today's session, I'm looking forward to have some more numericals, last few numericals as far as the unit load method is concerned. So quickly, let me go through it. So numerical example of application of unit load, today's session is dedicated to that. And here you can see that I'm not sure how many of you have collected your writing tools, because I'm not able to see you in the class also. And I insist that those who are there, those who have joined the session, please have your writing tools with you, so that effectively you can complete your numerical, which I'm going to share with you within the next few minutes. But before that, let's have a look on this text, like basics of the unit load method. One more thing I would like to tell you, that in case during the session we may face the break of the internet also, so don't go anywhere, because still the services have not been re-established completely at my end, since I'm at home. So I'm trying to connect myself through the mobile internet. That's the only solution. So I have tried it. I'm sure that at least for 1 hour it will not get damaged or break. But in case it happens, don't panic, and I'll again rejoin with you as soon as possible, right? So okay, let's go ahead. And basics of the unit load method or the virtual work method. Now you must know that unit load method is also known as the virtual work, because here we take only a unit value of whatever actions that we are considering. Either it is a point load or a moment. There are only two types of unit loads that we are going to utilize. We are not going to use any UDL for unit load. Please remember. So you either need to use point load or rotation, and you know the reason why, right? May I have answer to this question before we move ahead from any one of you, those who have already joined? Please tell me what is the reason that why we select only a point load or moment in this unit load method. Can anyone raise your hand? Those who have answered, please raise your hand, so that we can start the dialogue also. Two-way communication can be included in the online session, which is very important. So the question is very simple, that we have seen, we have also utilized that point load is used, the moment is used with one unit value. But why only these two? Why not the UDL? Why not the UBL likewise? What is the reason for that? Anyone from the class can answer to this question? However, it's very easy to answer this question. And no, I mean, language should not be a bar. Don't worry about language. You can speak in Hindi, you can respond in Gujarati. Also, if you are not comfortable with language, should not be a problem. I'm concerned with knowledge, not with the language primarily. So raise your hand, those who know the answer. Or let it be wrong. There is nothing wrong in, dialogue. Have a dialogue with all of your friends. We all are colleagues only, so don't worry, don't hesitate. But at least I need one response from your class. So raise your hand with some answer to this question, that why we use only a point load and a moment in this operations related to unit load method. It may be a guess also, that's fine. If it is a guess, again, it's fine with me. But at least I need a volunteer. Otherwise, I need to go to the names and then I need to tell what is the reason, right? So try it by yourself. Yes, somebody has raised the, Stephen is there. Yes, Stephen.
So I think it's because from the name itself for unit load method. So if you talk about point load and moment, you are basically talking about either a deflection or displacement in a specific direction. So due to the fact that a moment and a point load can only act at one point, and hence that's the reason why we're utilizing them, because we're specifically targeting the actions on a beam. Let's say for instance, like for a point load, they can only produce a deflection at a particular point where it's acting, and that's the reason why I selected. Then for a moment as well, a moment acts on a specific unlike the UDL where it has to act on the entire span.
Right. Perfect. I think it's nearly perfect answer, Stephen. So you did well. Thank you for discussion. And as we all have listened to Stephen just now, what he said that yes, definitely point load targets a point, and you know that deflection is related to the specific point also, right? So that's why we ideally select point load to obtain the effect of or symbolizing the deflection in the member. So that is the ideal load type to be used. That is first thing. So since point load is associated with deflection, deflection takes place at the specific location. And if you use the UDL, you are not certain about the location of the deflection, right? So then in that case, you need to have an equation. As you know, in case of UDL, when you are working with, you need to go for the equation, and it affects the entire length of the spread on the beam itself. So you are not so definitive, or you are not so fixed that at this location only you want a deflection. So that's why primarily we use point load to indicate deflection. And the second answer is regarding moment. Since moment creates the rotation, and we all know that we are interested slope. So in case of developing a slope at a particular location, we need to have moment at that particular location itself. So rightly said by Stephen, and we all are agree with him that definitely we can use moment for rotation because it is associated with it with a slope, and which creates a twist and slope into the structure. That's why you should use the unit value of rotation. And since the point load is indicating a deflection at a specific location, you must use the unit load for the same. So it's a great learning for every one of us. And with this knowledge, we can go ahead. So let's very quickly go through some of the salient points of this method itself. It is helpful to calculate the deflection slope in the determinate structures. It is useful for determination of the reactions, member forces. You know that once you have the reactions, you can definitely use the first principle of mechanics of solids, and you can obtain the internal forces like moment and shear force of the structure. One more point I would like to highlight here is you can not only use it for the determinate structure, but equally you can use it for the indeterminate structures. In sometimes when you take a ratio of the uh, quantities and the multiplication of m1 into m2 divided by m into m2, and if you take a ratio, you'll be getting the reaction values also. So that is equally possible that you use the virtual work method for determinate as well as indeterminate structure. However, looking at to our scope of the study right now, we are restricting ourselves with the determinate structures, but in future definitely you can use it for the indeterminate structure and calculation of reactions first instead of the direct slope and deflection. you can first obtain the reactions, and based on that, you can definitely get the internal forces also. So the primary equation remains similar to the energy principle, that is EI d square y upon dx square equals to minus capital M. That is the most, and integration within the 0 to L length, that is the common equation that we have in our hand, which we can utilize, right? So that doesn't change, that remains as it is. And now you know, with the working with the M, capital M, small m1, small m2, like that, what you have to exactly do over there, that also known to you, right? There should be a point load available at the point where deflection is required. Now we all know that. Similarly, a unit moment should be available where the slope is required, and it may be not necessarily available always at the end of the beam. It may be anywhere in the span. You can have any location to be selected within the span of a beam at any point of time, and any type of the load types. Ideally I'm speaking, because we have practiced with largely with the UDL point load and combination thereof, right? And a limited type of the structures we have explored, like cantilever beams and simply supported beams, we have explored extensively. We have also explored it on the frames also. Today I'm going to share with some of the numericals with the frame itself with you, so that you'll get to know more about it, how to solve them. And those I've taken from your reference book only, so you can later on confirm your understanding by reusing those numericals, once again revisiting the pages which I have already shared with you. So the generalized equation of a moment due to external loading is denoted by capital M, that you all know very well now, and generalized equation due to unit load is denoted by small m. So in case there are more than one quantity, you can use them like M1 and M2 also, and so on and so forth. So all these things are very well known to us. So from this, let's go ahead and we'll take a numerical like this. Earlier it was a plan to share this numerical. I would have been sharing this online, or I mean on a board, and you will be doing it in the class in front of me, so that you can also get to know the right way of solution. But anyways, since today's class is online, so I'm sharing this few numericals with you through this medium only. That's where we earlier we have done. So that is why I insist that all of you, those are if it's in your reach, please collect your writing tool and start writing this problem in your diaries, in your notes, and along with the discussion, as we progress, as we move ahead, you should also start working on that. It will give you an excitement also of doing something by your own self, right? So apply a point load without, this is the discussion over here. And before that, let's go through the question itself. You can see here, there is a cantilever. Of course, the varying moment of inertia to be taken into the consideration rigorously when you are giving a solution. There is a span difference between the two segments, 3 meters and 2 meters. So total length of this cantilever beam is 5 meters, having two types of loads. As you can see, one is a point load and second is UDL. UDL is having 20 kilonewton intensity per running meter, and you have a point load of 60 kilonewtons. So that is what is a given situation. We also have a moment, I mean flexural rigidity value, that is capital E capital I, that equals to 10 into the 10 to the power 13. So ideally 10 to the power 14, that you can have as a numerical value of EI. So determine the deflection at point B. So free end here, you need to determine the deflection and slope at point C. So you require slope at this value at this moment, and a deflection at this point B. Now, one question I would like to ask you qualitatively before we go ahead in this case, this is regarding the slope, right? So as it is mentioned in this numerical, this is a technical discussion. So as it is mentioned that you need to find the value of slope at point C. My question is, if I find slope at point B, right, will it be same to point C or will be different? My question is very simple. Let me repeat it again. I just want to know from your side, any one of you, that will the value of slopes at point C and point B will be similar or not, and what is the reason? If it is similar, again you need to tell me why, and if it is not similar, again you need to tell me why. So raise your hands, I will unmute you and you can share your answer. It's very interesting answer, the simple answer that you can think of. uh, Otherwise, as you know, yes, we have Vinay. Yes, Vinay.
Sir, it will be different as at point C there is a point load of 60 kilonewton.
Mm-hmm. And what about B? There is a UDL, right?
Yes.
So your
Yes.
answer, is perfect. Like there will be a different value of slopes at point C and point B. We all know that definitely. And here, likewise, in this case, we just need to focus on slope C only. However, in case if I once again ask you to find slope at point B, you will see the difference between both the values because there is a variation of loading. Please understand. So my point really actually was, if you have no loading in this area like point C to point B, then definitely you can say that there is no variation in slope again, because the in that case the tangential value will not be changing, the slope value will not be changing. Definitely the deflection will be the function of the length, so deflection will be different in any case, whether there is a load here present or not. Definitely you should understand that deflection is a function indirectly to the length also. Larger the length, more will be the deflection. So you cannot generalize deflection in the way in which we have generalized the slope. But definitely slope will not be changing any of its value largely if it is not seeing any variation into the loading conditions, right? So please understand this, register this in your minds so that you can use them in future also, right? It's a very important understanding on behavior of the structure. Okay, friends, so now I think most of you are ready, and Jeevesh, you want to say something, Jeevesh? Otherwise mute yourself. Okay, Jeevesh, thank you for muting yourself, and I understand that was may have done by mistake. Okay, so let's go ahead, apply a unit moment at a point C because we need a slope at point C. I'm just roughly discussing with the solution with all of you, and I'm sure that most of you have already begun the solution. So the beam will be divided into two segments. So Jivesh, again your voice is there. I'm afraid that I need to remove you from the class in that case if you don't take care. Mute yourself, Jivesh.
Just walking around.
So I'm sure that now there is no any more disturbance expected, right? I forgot to employ the restrictions, so that's why that was happened actually. Okay, so I think now we are through and through. Okay, fine. So friends, let's go ahead, and we were discussing that beam will be divided in two segments. BC segment will have origin at B, needless to add. I know that you know all this very well. CA will be the another segment, will be having origin at point C. The form of equation capital M, consider the only external loading. This is important for those who are still struggling with how to manage the capital M equation. So I insist that you write down these points in your notes before you start the solution. You need to create capital M equation for both segments, as you know from our earlier practices, B to C and C to A. And then you have to go for small m equation, m1 equation, that is due to the moment in the unit point load at point B, and a small m2 equation, that is a moment equation due to a unit moment at point C itself. So you can see that where we require deflection at point B. So at that point we have to apply unit load, and the moment where you require slope, you should apply unit moment itself. All right, so I think we are clear on this point, and let's go ahead. So this is the equation first to explore. Like we begin with the segment C to B. B is the origin. The length is 0 to 2 meter. And as you can see, there is a UDL only. We will apply a point load later on. But first, you have to create capital M equation based on the external loading. So here again, if I go back, here you can see that 20 is the UDL. So X starts from point B. So we are standing here somewhere here, right? If I take some pen here, we are standing here, and the X is to be considered from this origin, right? So this is the length. Now we have X, and this is a load already with us. So 20X is the total load, and that will be acting half somewhere here. So half of this will be X by 2, X by 2. So again, you have to multiply it with X by 2 term. So 20X into X by 2 gives you the value of 20x square by 2 itself. So this is quite understandable, and since it is negative because it is clockwise, right? So now there is a time to create one more numerical solution for equation, that is small m1 due to point load. Point load is only 1 unit and the distance is only x. So again, if I go back here and if I take it once again, here you are applying a point load, right? So the value is 1, and here you are standing somewhere again. So this force into this distance, that creates again the clockwise moment, so that is negative. So that's why we have taken it minus 1x. So M2 is related to unit load moment. So there is no moment applied right now because we are not interested in span at this moment. So we just go with 0, and there is a variation. So that is considered here. So I is nothing but the variation of the segment. So now let's go for the second segment where C is the origin and its length is 0 to 3 meters. Now you have to consider total load. So 20 into 2 meters is the earlier span, so gives you 40, and it is acting at the center again for, so that here you can see that x plus 1 because total length is 2, so half of that length earlier, and the x of the next segment. So if I go back here, you can, sorry, if I go back and write x here in a second segment, and this is the new x. Now you may find that in some solution books you will find this continuous x also, and in some books you will find x itself as per the segment. So that largely doesn't matter, but what we find that using the separate small segments gives you small equations, and those are easy to solve. So that's why we prefer to have different segments altogether. Okay, so I think you are okay with this. And now our unit load is this UDL is here because we are dealing with capital M equation. So 20 into this total length, so 20 into 2 gives you 40, and half of this is 2 meter. Here you can see this 2 meters, so half of this is 1, and then additionally x you have to add to reach here. So 20 into 2 into total effective distance x plus 1. So now I think you are clear enough that how the equation have been developed. And of course there is an external load of 60 kilonewton as a point load, and only the distance is x. So again it will create clockwise moment. So that is how we have developed this capital M equation in the second segment. Now we will focus on the deflection again. So deflection is occurred due to the unit point load, and we all know that it is in second segment. So earlier the 2 meter is the span of the earlier segment, which we need to include here. So x plus 2 minus 1, and m2 will be just a moment, unit moment. So there is no need to multiply anything with here, because I would like to demonstrate here how we have worked it out. Let's say uh, let me try to erase all this so that it becomes clear to all of us, and then we'll come back somewhere here. So taking a section here again, that is the x, right? And we have to apply unit moment here. See here, this is a unit moment, right? But it has no compulsion of multiplying any distance as such, because it is a unit moment. So you can apply it anywhere, like B to C, C to A. So even if it is working here, it doesn't require any multiplication of distance as such. So it is one only. So that's why you can see that it is taken as it is, negatives obviously, because it is clockwise. And without fail, you need to mention the inertia of that particular section or segment, I would say. So now I think you are almost ready with your calculation. So before I give you the solution, I give you 3 minutes, 4 minutes to work upon it. All are required. Those who are equipped with the writing tools, all are requested and advised to start doing calculation. You know the how to put them together in the equation form. So delta B equals to integration of first segment capital M into M1 dx, and plus, since there is a zero, so we'll not consider it, and plus delta B for second segment, that is this the larger equation, into M1. Do not multiply M2 at this moment, because M2 is pertaining to the slope only and not with the deflection. So there has to be a separate equation utilized for deflection, that is M into M1 for both segments. And when you will be dealing with the slope, we'll avoid M1 and we'll go to the M2. So we'll go with M1, capital M into M2 for slope later on. Right now, you can focus on capital M into M1 for both segments. Algebraically add them together after taking the integration of the given condition. But first you multiply these two things together and have a generalized format, and then you try to integrate it with the limit of 0 to 3, and that will give you some final answer in your notes, right? So I'll be giving you next 2 to 3 minutes now, and you try to work upon, and then I'll share with the rest of the steps for the solution. So here I'm leaving it up to you for 2-3 minutes only, so make it fast. And in case if you have the answer, please raise your hand in the chat box. So raise your hand, I will unmute yourself. So take your time, 2-3 minutes quickly, and work upon it. And as soon as you are done, raise your hand. So first we'll find deflection. So consider capital M in M1, small m1. So I'm waiting for your hand to be raised. So I'm here only, not going anywhere. So don't worry and stay tuned. Keep working for 2-3 minutes more, and then we'll see the solution. All right. So there is a good news that somebody has raised the hand. Darsha. Okay. Yes, Darsha. Birendra. Darsha, you can unmute yourself, I think.
Sir, I am getting 6.1 mm delta B.
6.1 mm.
Theta C is equal.
No, just deflection.
Okay, 6.1 mm.
Right. And okay, let's go to Birendra.
Yes, sir. Sir, I got 11.5 mm.
Deflection.
Yes, sir. Deflection.
All right. So at least people are trying. So that's a good news to all. And you are equally active on online mode also. So I appreciate a lot of this gesture. Let's go ahead and let's see. This is what is the obvious step that we need to follow. Like delta B equals to 1 upon EI 0 to L, that is the length, right? And sorry for that. As I said, all right. So let's go ahead and 1 upon EI, that is between 0 to 2 and 0 to 3 meters. We do have these equations as I explained earlier. So with this, we have laid down all the equations here, multiplied properly. So let's see. Moving ahead again, that's the same equation. Further, we simplify it. 0 to 2 meters, 10x cube. The term becomes positive, of course. And here you can see that without fail, you have employed 1 upon 2 EI. Please be careful about this. Sometimes you make a in some of the calculations error, small error, and we have to be very specific in that case. So let's simplify this again. When you multiply these two brackets, it gives you x square plus 3x plus 2 as an expanded term, and 60 square 120 into x, which is the multiplication of this simple step. So this is how we have obtained this 11.5 mm. So the people, those who have calculated this, must have think about correctly. So you are right. I think Birendra was having this answer. However, Darsha, I would like to advise you that please check your somewhere maybe a correction required. I'm sure that you have done a proper job, but somewhere you may have not considered the effect of either it may be a problem of small numerical error. So just correct it, please, and confirm your answer. That is 11.5. So let's move ahead. And now, before giving you the solution, just try with the theta C, slope at location C. So please work upon that and share your answer with me. I think those who are ready with their answer, please raise your hand. Earlier also somebody has raised their hand for answer at theta C. I think Darsha, you were ready with your answer, so you can raise your hand in case I can unmute. Yes, Darsha.
Sir, Sir, I am getting 0.00285 radian.
Okay, 285, 0.00285. That's what your answer is there. So we'll take it further. And is there anyone? Okay, that's fine, Darsha. Is there anyone would like to share? I think it was 0.00285. So anyone would like to share the other answer of theta c? Otherwise, we'll go ahead and let's do it, because most of you are not calculating in parallel. So here you can see that the first term becomes 0, so there is no point, there is no doubt about it. And in the case of second stage calculation, it is 1/2 ei. 0 to 3 meter is the length of integration, 40 into x plus 1 plus 60x. So when you do expansion of this, you get this expression 1/2 ei 40 x square by 2, because you need to integrate this term. So it gives you x square by 2, 40 becomes 40x, and 60x becomes 60x square by 2, right? And then you replace it simply with the final answer of integration length 0 to 3 meters. So it gives you 570 divided by 2, which turns out at 285 kilonewton into meter square. As we all know that slope is always expressed this as kilonewton into meter square, and the deflection is always expressed as kilonewton into, yes, m cube, right? So here that necessary changes you need to do. So yes, Darsha, I think it seems right. 0.00285, that is the perfect answer that you have obtained. And ultimately you can convert it into the degrees also by 180, multiplying it with 180 divided by 3.14. So that will give you the degree also in case if you want. However, it is not mandatory, but as a final answer, you can write in radians also, and in the degree you can also convert. So friends, I think we are all set with the other example. Quickly, we will take this example. I insist, really it is very interesting. It is a bent frame. You can see here, let me describe the some of the conditions, and I'll give you some tips also what you have to do. The instruction follows like you need to obtain the deflections only. There is no question regarding slopes, but deflection will be considered in two direction over here, vertical and horizontal. So we have a bent cantilever named as A to B and B to C. So naturally we will have two segments, C to B and B to A. Naturally their moment of inertia are also varying, like for 2 meter span of B to C have a single I, and for B to A you have two I here. The lengths are also different, like 6 meter and 2 meters. So total length will be 6 plus 2 8, of course. And you have a UDL only, right? There is only a UDL as external load on this frame. So we are dealing with the frames now, and 4 kilonewton per running meter is the intensity. What you have to do is find the horizontal and vertical deflections at point C. So needless to add, now everybody will know that what you have to do next. If you are interested in vertical deflection, place the unit load at this location in vertical direction. And if you are interested in horizontal direction, at this point, apply unit load. Yes, unit point load in horizontal direction itself. That is why we started the discussion with this important point, that why we use point load only, because see, this is the same case where we require deflections in two different directions. So that's why you have to use point load in that particular direction. So based on the application of the forces, your M1 and M2 will be different equations, because moments will be different for segments B to C and C to A for vertical force and horizontal force. However, there will be a common equation available to every segment in terms of external load. So capital M will be same, but M1 and M2 will be different, right? So those who are convenient for them, those who are writing or doing the work with me, so they should start their work. here we can see that we have been given with the values of capital E and capital I. So you can see, you can read it properly, that capital E value is 205 into 10 to the power 6 kilonewton per meter square, and the I value is also given in meter raised to 4. Please be careful in transferring the units. Please convert everything into the Newton into square format, right? So here when you do it, in the denominator you'll be having 6, and in numerator you have 3. So again 3 will be deducted from this power, so that is 205 into 10 to the power 3, and I will be 10 into 10 raised to minus 6, and that is to be added with 12, right? So m to the power 4, so uh, you have to convert it into the again. So 12 and 6, 18. So 18 and this 3 will give you 15, right? Because this is minus 18 and here you will get a plus 3. So it is minus 15 ultimately. One more 10 is there. So you can have 16, 10 to the power minus 16 and 205, right? So that is how you can convert it. However, I keep it with you. You are completely free to convert it at per your convenience. But now let's try. So I'm revealing the equation first of all for you. Naturally, M1 and M2, M1 goes with the vertical, M2 goes with the horizontal deflection. Again, you need to create one more table of I and 2I. Why I'm directly sharing this with you, because now you must have acquired the skill enough to develop the capital M equation, small m equation. Here you can see 0 is mentioned. So why it is so? Because in second case, M2 is dealing with this equation. So this is the force which is in a line of member C to B, where there is no force line, right? So there is no force actually which of which you can take a moment. So M2 equation will be 0 for this segment, and that's what you can read from this table also. When you go to the next segment, B to A, so earlier this was the case where you need to take a section here for capital this thing. This was the first segment, so X will be here, and when you come down, the X will be here in this direction, right? So somewhere here you need to take moment of this UDL. So this UDL will be in second case it will be totaled 4 into 2, right? And it will be directly working on this second segment, right? So for first segment it will be 4 into x square by 2, and for second segment it will be 4 into 2 into 1. So that will be the total moment that you need to transfer here. When you come here for this was the story for capital M, the just now what we have discussed. I'm writing with mouse, so my writings may not be up to the mark. So M1, this is a condition for M1. We are standing here. Your X starts its journey from here. So 1 into X. So that is a moment here. And for this segment, when you come again, the X will be lying somewhere here, right? So this is the X value, X distance. But here is the force. So it has no relation with this direction, but however, you can take moment of 1 into 2. So 2 will be the direct moment applied for second segment, just like in this case. Total load into the distance that was created as total moment. So here again, you have total moment due to this unit load. And in this case, there is no as such moment for this, but when you come down, when you come here, take a X distance like this, there is a very well possibility to take moment of this force 1, and perpendicular distance is X. So here for the entire beam, it will be X itself, or ideally 1 into X. So just an X. Again, it will be minus since it is clockwise. Again, this all values will be minus negative because it is again a clockwise moment. So let's go ahead. Here you can see everything is taken negative, and this is what is the I value that you can spot here. For second segment, don't forget that it is 2I. For first segment, it is I. So now I'll be waiting quickly, those who can complete the calculation. First, you tell me the vertical deflection, and then you tell me the horizontal deflection. So for vertical deflection, let me advise you, you have to use these two things together. Capital M and M1 will give you delta V at point C, and capital M into M2 will give you delta H, right? Horizontal, because it is horizontal force. This is derived, which we have derived due to the horizontal force. This we have derived due to vertical force, and this is due to external loading itself, right? External loading. Okay. So I'll be waiting for a couple of more minutes from now, and meanwhile you can share, you can raise your hand, we'll have your answers, and then we'll go ahead quickly. So 2-3 minutes practically maximum. Try them, try it. It's very easy. The first segment anyhow is going to be 0. So only the second segment you need to treat for sigma, I mean a vertical deflection. So try it and raise your hand once you are done. Don't hurry up, because in rush, you may miss out some of the important calculations. Do not forget again to include 2I in your calculation denominator. And I'm sure that most of you have entered yourself in the chat box for attendance. If you have not done it, please do it, because today the only way of taking your attendance is the chat box. So if you have not done it, please without fail do it. Right now you can first do it and then you carry on with the calculation, because I can see only a few messages are there in the chat box. So nearly 27-26 students are present at a time. So please enter your details very quickly in the chat box, everyone, please, so that I can take your attendance. Remember that if you don't register yourself in chat box, it will be difficult for me to identify whether you have attended the session or not. And that's the only source for me to take attendance. So without fail, write down your name and details in the chat box, and then you carry on with the calculation. And those who are ready, please raise your hands. Okay, I can see two raised hands. Darsha, let's go to her. Yes, Darsha, and then we'll go to Henry.
Sir, vertical deflection is 27.32 mm.
27.32 mm. Okay, stop there and we'll register it. And 27 point, what was that?
32.
32. Let me ask to Henry. Yes, Henry.
So I'm getting the same answer, 27.3 mm. Yeah.
Excellent. So there are good possibilities that it will be correct from each of you. So let's go to that. Thanks for discussion to both of you, and let me see whether it is All right, so it seems okay because 27.3 is the right answer for vertical deflection. I think all of you are agree with this calculation. Here you can see as how simple it was. Like it was very obvious that you will be getting the right answer only, and every one of you have done correctly. I take it for granted. So vertical deflection is 27.3 mm. So now who would like to share again the horizontal deflection? Yes, Darsha or Henry or Birendra or those who are the regular. Okay. Yes, Darsha.
Sir, 35.12 mm.
35.12 mm. Okay, let me go to Birendra. Yes, Birendra.
Yes, sir. 35.1.
35.1. Can I have somebody else from the class who would like to share their answer? Please don't hesitate. The only thing is it may be incorrect, that's it, but at least you should say that you are working on your numericals, right? So don't hesitate whenever it is chance given to the entire class, and do not left behind and share your answers. Let it be not exact answer, that's completely fine, we understand that. So anyways, let's confirm it from our end. uh, so that is 35. Okay, I'm right now unable to see it exactly because there is a window which is disturbing me, but I'm sure that it is 35 point something is there, 1 mm. So that's fine. So most of you were near to the answer, correct answer. Now one more question is there, why delta cv is less than delta ch? So why horizontal deflection is more than the vertical? Anyone would like to comment on this? This is what we should do every time, because see, getting right numerical answer doesn't give you all the knowledge. So you should also focus on the behavior of the structure also many a times. Why this deflection in because if you notice, we have not changed anything. Am I right? So I have not changed any external loading for vertical or horizontal calculation. Even we applied unit loads in both cases. So what should be the reason? What should be the reason according to you why the horizontal deflection is more compared to the vertical one? And now you are free to raise your hand. I will simply like to listen to you. Anyone would like to answer this question quickly? Think over it for 1 minute and answer me. Otherwise, I will reveal the behavior. And that is what is our concluding session on unit load method as well, because I want to start ILD in the tomorrow session. But before that, this is very much important to learn about the behavior of the structure. Who would like to comment on that? Let it be wrong, as I said earlier. That's completely fine, and you may be right also. So we never know. So let me have your raise hand. Any one of you, please raise your hands in case. Why? The question is simple. Why horizontal deflection is more than the vertical? For that, let me give you a tip. You need to relate, as I said earlier, if you remember, the deflection is a function of length. Please remember, we begin the discussion with this argument that slope is not a function of length, but definitely the deflection is a function of length. So it is very obvious now for you to find the answer of this question. Why vertical deflection is less than the horizontal one? And I'm sure that you may have heard the term called slenderness also. Slenderness is what is a property of a material or the component where the length ratio to the lateral dimensional ratio is taken, and more the slenderness, more the flexible of the member, and more unstable also. So which is the, I'm slowly giving you the answer, or let me correct the answer now, since you have not raised the hands over here. Let me explain it very graphically and very quickly. you can see that segment, C to B, right, having length of 2 meters only, right, and it will show the deflection like this. Okay, this is a vertical deflection. So vertical deflection is a function of this length, which is rigidly connected and supported by the vertical arm over here. So this is the functional length for this deflection, delta V, right? So it is, definitely not having a larger length, and it is not as slender as compared to the another arm, that is B to A. Finally, you have a support at point A to B, so which is more slender than this area. And when you consider horizontal force like this, not only the segment CB, but the entire structure will see the deflection like this. So again, I'm drawing here just to explain you the overall behavior of this. Sorry, the graphical explanation goes like this, because this deflection counts more. This is horizontal deflection, right, in this direction. So you can see that the lever arm increases, the slenderness increases, the length also increases, even though the moment of inertia was double than this. You may think of it, earlier, here in this case, the moment of inertia was I only. Here it was again 2I, but compared to the length, it is just 2-meter length, and here you have 6-meter length. So you can very well understand why the deflection in horizontal direction is more compared to the vertical direction, and that is called property of a structural member known as slenderness. And slenderness provides you tremendous stability. So less the slenderness, more will be the stability. More will be the slenderness, less will be the stability. So here the slenderness increases with the function of the length, being the function of the length, and that's why you notice that the horizontal deflection is larger than the vertical one. So please understand that numerical answers will not only the way of getting the knowledge about structural behavior. There are a lot of other factors you need to think of. Even if I change the orientation of the members used in this member, and if I incorporate the let us say this, let me try it to show you what I mean to say is, right now if I'm using this cross section in my frame, right, if this is my frame, if this is the cross section which I'm trying to mention over here, right, and if I take it as it is, right, and if I apply unit load, there will be a deflection of this member. And if I change this orientation from horizontal to vertical, like if I change it like this, pardon me, I'm using this area just to demonstrate it, you can again very well see that where it will impact, right, it will impact on where, it will impact on moment of inertia itself, because now in this case you have tremendous depth of this section, right. So orientation we generally avoid at this moment. That's why we take it I as constant for both cases. Here you can see, but the moment I change their orientation, definitely this values, both values like horizontal and vertical, will largely get affected. So this is the bottom of learning, that you should relate your numerical answers with the behavioral aspects of the structural elements, right. So friend, like this you have to keep relating your understanding and level of knowledge. Whenever you are getting a new information, you should start comparing it with the already known things to you, like these things are already known to you, right. But now in this case, let us say point A and point B. So definitely for a same loading itself, the deflection in point B will be far lesser than the deflection of point A in this case, because of the limitation of moment of inertia cross-sectional orientation. So orientation of the members are very important for any structural arrangement, so that you have to take care. So friends, I think it's a good time to stop today, and in tomorrow's session, we'll come together again for learning the new content on the ILD. That's I'm going to start the basic discussion, and I will take it for granted that couple of knowledge is already with you. So I'll not bring you to the very historical background of ILD, but definitely you need to answer some of my questions. So get ready for that regarding the initial introduction part for ILD. And then we will see how to solve ILD, I mean, structural problems with ILD for structural assessment of the indeterminate structures. Eric, yes, Eric, tell me.
Yeah, excuse me, sir. May you show the previous slide for that frame? There is some information I missed.
Okay. Previous slide you want to go. Is it this?
No. Before this one, for the question.
Okay. Is this?
Okay, thank you. Yes,
Okay.
sir, thank you.
And even let me remove this writings. Will give you clear pictures so that you can easily write what you want. So I like the way in which you are interacting with me. It shows that how much you are interested, how much you are attending the sessions. So I really appreciate not only few students, but I appreciate all that everyone should take equal interest, whether you are doing the work parallel to the ongoing work or not. That is another thing. But ideally, if you work parallel with me, it will give you another excitement of doing the work together. So if it is possible and if it is allowed, then we'll meet in the offline mode tomorrow. Otherwise, again, whenever there is a possibility of point of contact, we'll come together in the online and offline dual mode also. So largely it's going to be a dual mode. So those who are going to come attend the college tomorrow will meet in person, and those who are attending online will meet online again on the stipulated time academic schedule of tomorrow's class. So tomorrow we'll start the discussion on ILD for indeterminate structures. So till then, keep practicing and take good care of yourself. We'll meet again in the next class. Till then, take care and thank you for joining this session. Tomorrow we'll meet again. Thank you.